Welcome to this comprehensive guide for beginner Unity programmers, focusing on converting coroutine-based systems to the async/await task pattern. This conversion aims to significantly improve code readability, enhance efficiency, and provide greater control over asynchronous operations within your Unity projects. First, let's understand the fundamental differences between coroutines and the modern async/await pattern. Coroutines are special functions in Unity that can pause execution and resume later, allowing time-based operations without blocking the main thread. They typically use IEnumerator and yield return statements to control their flow, making them tightly integrated with the Unity engine's lifecycle. Async/await, on the other hand, is a C# feature that simplifies asynchronous programming, making it easier to write non-blocking code. It uses the async and await keywords to handle long-running tasks without freezing the game, offering a more structured approach. Async/await improves upon coroutines by providing better error handling, the ability to return values, and more flexible control over execution. Let's delve into the key differences. Coroutines cannot directly return values, while async methods can using task t. Error handling is simpler with try-catch blocks in async/await, compared to the more complex error management in coroutines. While coroutines run exclusively on the main thread, async/await can run on separate threads, preventing blocking and improving responsiveness. However, it's important to note that WebGL support is generally better for coroutines, and async/await can sometimes have issues with WebGL builds. Code readability often improves with async/await, as nested coroutines can become quite complex and difficult to follow. Async/await also offers more granular control over asynchronous operations, whereas coroutines have more limited execution control. Cancellation is another key area. Async/await can use cancellation token for easy cancellation, which requires specific implementation for coroutines. Performance can vary. Coroutines can be less efficient in certain scenarios, while async/await is potentially more efficient but can generate garbage. Unity integration is tight with coroutines, but async/await requires more manual management to ensure proper interaction with Unity's single-threaded nature. Now, let's begin the step-by-step conversion process. Our first step is to identify the coroutines in your project that you wish to convert. These are typically functions that use IEnumerator as their return type and contain yield return statements. Next, you'll need to import the necessary namespaces. Add using system, threading, tasks to the top of your script to enable async/await functionality. The third step involves converting the function signature. Change the function's return type from IEnumerator to async task if it doesn't return a value. If the function returns a value of type t, change it to async task t. Remember to add the async keyword before the function definition. For example, an original coroutine IEnumerator mycoroutine becomes async task myasync method. Our fourth step is to replace yield return statements with await calls. Replace yield return null with await task, yield, to wait for the next frame. To replace yield return new wait for seconds, use await task, delay. It's crucial to remember that task, delay uses milliseconds, so you'll need to convert seconds to milliseconds for accurate timing. For Unity's asynchronous operations like async operation, such as loading scenes, you can directly await them. You can also use a while loop with await task, yield, to wait until the operation is done, as shown in this example. Step 5 addresses handling return values. If your coroutine returned a value, modify the async function to return a task t. Then, simply return the value at the end of the function, just like a regular synchronous method. The sixth step is calling async methods. When invoking an async method, use the await keyword to wait for its completion. If you need to call an async method from a non-async method, you can use .getAwait or .getResult, but exercise caution due to potential exceptions. Step 7 focuses on error handling. Always use try-catch blocks to handle exceptions gracefully within your async methods. This ensures that any errors that occur during asynchronous operations are caught and managed, preventing application crashes. For example, debug.logError can be used within the catch block to log the error. Step 8 introduces cancellation. Utilize cancellation token to cancel long-running tasks if they are no longer needed. This is particularly useful for operations that might become irrelevant, such as when a user navigates away from a screen. You can check token.isCancellation requested and throw a task canceled exception, or simply return if cancellation is requested. Step 9 covers thread safety. It's critical to ensure that all Unity API calls are made exclusively on the main thread. If you use task, run to perform work on a background thread. Always switch back to the main thread before updating Unity objects. This can be achieved by using await task, yield, which effectively returns control to the main thread. Finally, Step 10 advises using async task instead of async void for most scenarios. Except for event handlers, async task allows for proper error handling and avoids potential crashes that async void might introduce. Beyond these steps, there are important considerations to keep in mind for optimal implementation. Performance is key. Async/await can introduce some overhead due to state machine generation and garbage collection. Always use Unity's profiler to monitor performance and optimize your code as needed. Regarding threading, remember Unity's API is not thread safe. All Unity-related operations must be performed on the main thread. Use task, run to offload heavy computations to background threads, but always switch back to the main thread to interact with Unity objects. Consider using Unitask, a library that provides an efficient, allocation-free async/await integration specifically for Unity's single-threaded environment. Unitask can significantly improve performance and is designed to work seamlessly within Unity. Unity also provides the awaitable class as an alternative to task. It's more efficient but has limitations, such as not being able to await multiple times on the same instance. Proper exception handling with try-catch blocks is paramount to prevent crashes and ensure a stable application. Utilize async/await for I/O operations like network requests and file access, as well as other long-running tasks. When deciding between coroutines and async/await, use coroutines for simple, time-based tasks and animations. Reserve async/await for complex asynchronous tasks that demand better error handling and more precise control. Let's look at some illustrative examples. Here's how to load assets asynchronously using async/await. The load asset async method uses resource request and await task, yield, to wait until the asset is loaded. Another common use case is performing a network request. The getWebPage async method demonstrates this. It uses Unity Web Request, get and await request.sendWebRequest to fetch data from a URL, including error checking. By following these steps and considering these important factors, beginner programmers can effectively convert coroutine-based systems to the async/await task pattern in Unity. This transition will lead to cleaner, more efficient, and better performing code within your Unity projects.